Computer Science and Engineering, moderator for this session. On behalf of Ashoka fraternity, I welcome everyone on this online platform for technical session 3 and 4 in 1 week online FDP on recent trends in computation, data processing and security, organized by Computer Science and Engineering Department. Today is third day of online FDP and the topic for first session is fundamental problems of algorithm and their parallel solution, which will be delivered by Dr. Ravi Shankar Singh. And second technical session will be on the topic smart grid security threats, which will be delivered by Professor Dr. Sharika Srivastava. Now we start with the first technical session of the day on the topic fundamental problems of algorithm and their parallel solutions by Dr. Ravi Shankar Singh. But before that, it is my honor to introduce our esteemed speaker to our participants. Dear Dr. Sir, Dr. Shankar Singh sir is currently working as an associate professor in the Department of Computer Science and Engineering, IIT BHU Varanasi. Sir has more than 20 years of academic and research experience. His research interest includes algorithm and high performance computing. Attended more than 25 conferences along with 2 books and multiple book chapters. Under his guidance, 7 students have been awarded along with 5 students are pursuing doctoral degree. Moreover, 14 students have completed and multiple students are doing their PG dissertation under his guidance. So, now I hand over the session to Dr. R.S. Singh, sir. So, kindly proceed with the session, sir.
Okay, thank you so much, Dr. Kavita. So, first of all, I would like to thank the organizers for inviting me to this virtual FDP. So, as I just came to know about the participants, that there are participants from non-CSE background as well. So I'll try to keep the things in very simple way. So whenever anyone feels any problem, okay, he or she can okay, interfere me. I do not have any problem with that. Now I am going to share my screen. So is my screen visible to all?
Yes, sir.
Is it okay? Fine.
Yes, sir.
Okay, thank you. So as I have kept the title fundamental problems of algorithms and their parallel solutions. So basically we'll be talking about sequential algorithms here. Okay, and there are some fundamental problems like searching, sorting. Okay, that so we deal with these problems in almost every bigger problem, or you can say any scientific or engineering applications. So we'll be let me go to the next slide. So I'll be talking about serial computing, then I'll discuss a bit about parallel computing, and then there is one famous model for designing and analyzing algorithms. Okay, a RAM model. So I'll talk about that. After that, I'll move to PRAM model, which is mainly for parallel algorithms, and then we'll see some fundamental problems and their solution using PRAM model. And after doing PRAM algorithms, you can say, we'll move to parallel algorithms for message processing models like MES, Hypercube, Bandit. Okay. So let me talk about serial computing. So whenever we write a computer program, there is some algorithm behind that. And if you take the algorithm, so we define the term algorithm as step-by-step procedure to solve a problem. Fine. So in an algorithm, what is there? There are certain number of steps. You can say finite number of steps. Algorithms have certain characteristics, like your number of steps should be finite, number of inputs should be finite, number of outputs should be finite. Okay, so there is one important characteristic. Uh, we call it characteristic of algorithms. We call it finiteness. There are other characteristics as well, so I'm not going to discuss that. So when you write an algorithm, what you do? You write certain steps to solve a problem. Fine. Now, corresponding to a step, there is a series of instructions. Okay. So, like if you are writing for I is equal to 1 to n, you okay, it's just this is step one, let's say, of some algorithm. But when you be going to instruction level, you will find many things, like we are doing some comparison, we are doing some increment. Okay, there are other operations as well. So we have a series of instructions, you can say, corresponding to a step in an algorithm. Now, in serial computing, what we do, we take these discrete series of instructions one by one. So at a time, what we do, we execute one instruction. Why is that? Why is that? Because we have only one processing element in our serial computing. Okay, so only you can. The bottom line is only one instruction uh, is executed at any moment of time. Fine. So let me go to the next slide. Now I have kept a diagram here to explain the things. Okay, so you have a problem. Let's say you have a fundamental problem. Okay, so let that be finding largest in a list problem. So basically, you are given a list containing n elements. What you have to do? You have to find the largest. Okay, so there are many ways to solve a problem. There is always, you can say, n number of ways to solve a problem. You don't know. You may be knowing 2, 3 methods, but there would be other people who would be knowing other methods. Okay, so for solving any problem, you can have a number of methods. Fine. So now the problem that I told is the uh, is a fundamental problem, and that's just finding the largest problem. So what we do, we write an algorithm to solve this problem. Fine. So I'm just going to take one method where what we do, we take the first element as the largest element. Okay, and now what we do, we compare this particular element that we have taken as largest with the elements present in the list. So what we'll do, we'll compare our largest with the next element. So suppose next element is larger than the previous one. Okay, so previous largest, you can say. So in that case, we'll change our largest to new largest. Second element will be the new largest. So then we'll be comparing the largest again with the next element. We'll move like that. Okay, so what basically we are doing, we are making certain comparisons. So corresponding to every comparison, there are certain instructions. So as I told that whenever we do serial computation, we have a single processor unit. So for understanding it better, you can consider there is a CPU. Okay, central processing unit with a single processor, right? So there is one and only one processor. Nowadays we have multi cores even in our mobile phones, tablets. Okay, so here things are being kept in theoretical way. So just assume that there is a single processing unit. Okay, so now what we are doing here, we are giving instructions to our CPU one by one. Step at time t1, we are giving first instruction. Then you can say we are giving second instruction. So we give the instructions to the processing element one by one in serial computation. Okay, so There will be, you can say, at most n minus 1 comparisons. Okay, so in any case, it is going, those who are from computer science background, for them it would be very easy to get the order of this algorithm as big O of n or theta n. So I'm not going to that thing. Okay, so now this is just, I'm going to an analogy. Okay, so you can understand the things like this. So suppose there are 1,000 answer sheets to be evaluated and there is only one teacher available to evaluate the answer sheet. So what that teacher will do, he or she will evaluate one answer sheet at a time. Okay, so after evaluating the first answer sheet, the evaluator will move for this second answer sheet, then third answer sheet. So this is how the sequential or serial computation uh, takes place in uniprocessor system, you can say, or in sequential algorithm. Now let's see parallel computing. So let's go back to our problem, the analogy that I have taken in previous slide, and that is evaluating 1,000 answered sheets. Okay, so let's say ideally one teacher is taking 10 minutes to evaluate one answer sheet. Okay, so since the examiner is taking 10 minutes to evaluate one answer sheet and 1,000 answer sheets are there, so ultimately he or she will take 10,000 minutes. Fine. So now ultimate objective here when we do parallel computing is to reduce the execution time or running time, or with respect to the analogy that I have taken, you can say the objective is to reduce the evaluation time. Okay, so what we'll do then, we will okay, we'll take 10 teachers, we can have 10 teachers to evaluate the answer sheets. So we'll give 100 answer sheets to one evaluator. Okay, so now what they will be doing, they will be evaluating these answer sheets parallelly. So we can do similar thing, and now you can reduce the, you can say, evaluation time by 1/10. So earlier, evaluating the answer sheet, uh, okay, we took 10,000 minutes, but when there are 10 teachers, you can say you can do it in, okay, 1,000 minutes. So you can say a speed up of 10. So now similar thing happens in parallel computing. So what do we have this time? In parallel computing, we have more than one processing element. Again, just for simplicity, I have kept here 4 CPUs. Okay, so what do we have? We have 4 CPUs to work on a problem. These CPUs may be working on different problems at a time. Okay, so you can have, you can deployment of these CPUs for one problem or more than one problem. So let's say that it is just finding largest problem in a list, and this time our list size is very large. Okay, let's say we have some 1,000 elements, and we have to get the largest of these 1,000 elements. So what do we have? If there is only one CPU, okay, then what will happen? We'll be comparing our largest to the next element, then again largest with the next element. We'll do like that. If you'll go to its code, you'll have something like largest is equal to A1, and then for I greater than largest, we are making largest as AI. Okay, so so we'll do like this with uniprocessor system. But when you have 4 CPUs, how you'll be doing it? So what you can do, you can have data decomposition. You can divide your these 1,000 elements in 4 parts, as there are 4 CPUs. Okay, and you can ask first CPU to get the largest of first 250 elements. Then at the same time, you can ask uh, second CPU to uh, find the largest of, okay, the second part. So ultimately these 4 CPUs will work simultaneously, okay, and we'll get largest for each part. Okay, so finally what is there? We have four largest values from different parts. Okay, 4 different parts. So now what we have to give? We have to give the final largest. What will be that? So we can either again we can either take 2 CPUs or three, all these CPUs to get the largest of 4 elements. But why to do that? We can ask it, since it is the problem size is very small, so we can ask this first CPU to do it or master CPU to do it. Okay, so in this process, what you can see, you can observe that a problem is broken into discrete parts that can be solved concurrently, and each part is further broken down to a series of instructions. Fine. So this is very basic introduction of parallel computing. Now, uh, this HPC stands for high performance computing. Okay, so let me define it. So any computational technique that solves a large problem faster than ordinary system, any ordinary system, is what? High performance computing. It has got various paradigms like parallel computing, distributed computing, grid computing. So I'll discuss about these paradigms very briefly, because I have to cover the fundamental problems, some fundamental problems, and their parallel solution. Fine. So basically, in high performance computing, our objective is to increase the flop count. So now is flop basically stands for floating point operations per second. Okay, so let's say there is a supercomputer, and it has some flop rating. So like IIT has one supercomputer that its flop rating is about 800 teraflop. Okay, so I'll tell about the order of this tera, mega, giga, and all that in coming slide. So basically, what we did there, what we have in a supercomputer, we have more than one CPUs, we have more than one node, we have okay, and we have many such nodes. So ultimately, basic objective is to have more number of floating point operations per second. So how to do that? Either you can deploy more than one processor to work on same problem, or your processor may be working on related problems. So now how to measure the flop rating or flop performance of a high performance computer? So for that, thus just here I have written mega flop. It is of 10 to the power 6 floating point operations per second. Similarly, gigaflop goes to 10 to the power 9 floating point operations per second. So whatever desktop you have in your black, okay, they are of gigaflop rating. So teraflop, we have at IIT BHU, we have a teraflop, okay, as I told, 800 teraflop supercomputer. But these days, supercomputers, okay, uh, are also a petaflop. Okay, so they are capable of doing 10 to the power 15 floating point operations per second. So if you want to know more about these top 500 supercomputers, you can visit the web, this top500.org for that. Now, this as I told that we have one Param Shivaya supercomputer. So it is around 800 teraflop uh, order. So now how to measure this flop rating of a supercomputer or high performance computer? Let's see that. So you know that most of the times our CPU clock speed is either 2 gigahertz or 3 gigahertz or around that. Okay, so I am taking one sample, okay, where we have CPU clock speed as 3.06 gigahertz. Now I hope you may be knowing about pipelining concept. So in pipelining, what happens? We are capable of performing some some stages parallelly. Okay, so let's say that that is 4. So we are capable of doing 4 operations like phase, decode, execute, write, back. You can say at a time. So now there is a processor and it has 6 cores. Like your mobile, if it is a if it has a quad core processor, then there will be 4 cores. So with a processor, how many cores are there? There are 6 processors. So now there is a node and it has two processors. So as I told that each processor has 6 cores. So we have two processors per node and number of nodes is 20. Okay, so what happened? We have built a high performance computer that has 20 nodes. Each node has two processor. Each processor has 6 cores, and then you can see here operations per cycle and clocks. So what we have to do ultimately for getting the clock rating of your high performance computer, we have to just multiply these, okay, and we'll get the theoretical flop estimate as 2.93 teraflop. Fine. And you see, this is the theoretical measurement. Ideally, we don't have 100% efficiency. So if you take efficiency as 85%, so your you can say your real life performance rating will be 2.5 teraflop. Okay, so you'll be able to run 2.5 okay teraflop operations per second. Now, one of the high performance computing paradigms is cluster computing. So you can build a cluster in your lab very easily. What you have to do for that? You have to just interconnect some ordinary computers, okay, with the help of fast switches like gigabit, Ethernet, MiriNet, or InfiniBand, or you can use fiber channels as well. So now since there are more than one computers, so ultimately they would be working on some problem, maybe related problem or maybe same problem. So the processors in different systems need to communicate. So this communication uh, will happen by passing messages. So you can see here, you can, okay, if you are not worried about the performance or throughput, just you want to set up a cluster. Okay, so you can take an Ethernet switch and connect your computers with that. And then obviously there will be certain libraries you need to install on your system and you can build a cluster. So now advantages over most other forms of high performance computing. Uh, I'm talking about the advantages of this cluster computing. So this is very highly scalable. So you can add latest processors easily. You can incorporate uh, a new node, or you can add n number of nodes anytime. Okay, that is not a big challenge in cluster computing. Your system will obviously become fault tolerance if one or two systems okay had some issues, okay, had some communication fault or hardware fault or software fault, you would be able to successfully run your application on other systems. And one important thing in this cluster computing, and that is your memory is not shared among the machines. So, okay, the next paradigm of this high performance computing is distributed computing. So, what do we have? You can say this distributed computing is superset of cluster computing. So, in distributed computing, basically your computers are so again, since this distributed computing is a superset of cluster computing, so you can uh, say that your distributed computing will is highly scalable and it has fault tolerance, redundant machines. Okay, to work on a problem, so you have a fault tolerant system. Now, under this high performance computing paradigm, we are this there is okay these days this is very popular where we have cloud computing as well. So what is there in cloud? Cloud uses internet and central remote servers to maintain data and applications. So you can avail various types of services like software, infrastructure, or platform. Okay, from cloud service providers. You can okay, and for accessing a cloud, you simply need a web browser or certain desktop or mobile apps. So you can see here this figure that there are there could be other types of services as well, but just to so that okay these are main important services of clouds these days. So application, platform, infrastructure. So you can you can go for availing the services of cloud, either using servers or tablets or mobile phones or laptop or desktop or any other such devices. So now there is one important thing when we study parallel algorithms, and that is speed up, or when we study parallel computing, and that is speed up. So let me define this term. So let's say there is some problem for which there is a sequential approach that takes TA time. Okay, you have written some algorithm, some method, some program. Okay, and it takes TA time. Okay, and the program or method has been written for uniprocessor system or for single CPU. Okay, now what you are doing, you are writing a parallel program. You are writing a parallel method. Let's say that V is the name of the parallel method. So, and we can simply say that TB is the running time of our parallel method. Running time, or if you are going for execution time, okay, then here also you have to take TA as execution time of your sequential program. So simply the speed up is going to be the ratio of TA and TB. So theoretically, this speed up can be given in terms of the computational steps using single processor divided by number of computational steps using P processors. Fine. So there is one famous law of for deriving the speed up given by Amdahl. Okay, so whenever you write a parallel algorithm or parallel method to solve a problem, okay, there will be some steps, okay, that are not at all parallelizable. Like you can take the analogy of evaluating the answers sheets. Okay, so when there are 1000 answer sheets to be evaluated and there are 10 teachers, so there is something sequential. Okay, not everything parallel, like so someone has to distribute, first of all someone has to distribute the answer sheets to these 10 teachers. Okay, so we can't do, if this job can also be done in okay, parallel, but there will be a step when the one person will be working, or so there are coordinating the things. Okay, so similarly whenever you are writing a parallel approach, a parallel algorithm, okay, there will be some steps that are not parallelizable. Okay, so let's say that f is the fraction of the steps that cannot be parallelized. Fine. So we can give the maximum speed up as 1 divided by f plus 1 minus f divided by p. So now why are dividing 1 minus f by p? See, we can say that 1 is the time taken by the sequential method, and then f is the part, okay, that is non-parallelizable. So we are writing that, okay, we are so, and plus what, there are other steps that are parallelizable, so that fraction is obviously 1 minus f. So since there are p processor and we are able to distribute our work here, we have ideal conditions, so we can say that we have informed distribution. Okay, so we are dividing 1 minus f by p. So max the this particular expression was given by Amdahl, so it is also known as Amdahl's law. Fine. So now let's see the maximum speed up. Okay. So suppose we are able to write an algorithm, a parallel algorithm basically, where every step is parallelizable. Okay. So what will be the value of f? Obviously it will be 0. F stands, as you can read from here, f stands for the fraction of the steps that cannot be parallelized. Okay. So so what we have in our algorithm, we have uh, everything parallelized. So f becomes 0. Fine. So you have to just put f at 0. We'll be getting S max as p. P is what? P is the number of processors. So this theoretically, you can say that the maximum speed up is equal to number of processors. Or in case of evaluating the answer sheets, your speed up is 10 if you are deploying 10 teachers to evaluate. Fine. So this parallel computing has lots of applications. There are okay. Uh, with I'm not going to detail of this. I'm just reading the applications of parallel computing. Okay, so for weather and climate modeling or prediction, we need high performance computers or parallel computers or supercomputers. For there are some time critical applications like chemical and nuclear reactions. We need high performance computers. Similarly, for biological and human genome modeling, we need parallel computers. There are other you can say applications listed here for which we need parallel computers. Okay, there are some commercial applications as well, so you can read them here. Okay, so for parallel databases or data mining, or take your Google search engine. So there are many high performance computers behind your Google search, every Google search. Okay, so web search engines, computer aided diagnosis in medicine also require high performance computers. So let's leave this as our important part is to deal with fundamental problems and their parallel solution. Okay, so I'm leaving one or two slides here also. Fine. So I have come to PRAM algorithms. So now we have to visualize something different from the figure okay given here. So there are you can see that there are n plus one processors accessing shared memory. Fine. So processors are being represented from P0 to Pn. So P0, P1, P2, P3, these Pn are connected to this shared memory. Fine. So what you have to visualize? You have to visualize that this P1 to Pn are not there. Only this P0 is there. Okay, single processor is there, and obviously if the memory component is there and no other processors are there, nothing is being shared. So we can consider the second block, memory block, as just ordinary memory block. Okay, not a shared memory block. Fine. So when you have this figure in mind, where you have just one processor and a memory connected, then uh, that is RAM model of computation. Okay, basically that is RAM here stands for random access machine. Okay, so mostly you know that RAM stands for random access memory, but when we study design and analysis of algorithms, sequential algorithm, be it parallel algorithms or sequential algorithms, okay, RAM stands for random access machine. So in your RAM model, what do you have? You have a processor, you have memory, they are connected to each. Link is bidirectional. Why bidirectional? Because our processor is capable of reading a cell of the memory, okay, and as well as our processor is capable of writing in any cell of the memory. Okay, so we have such RAM model. Now I hope you have visualized the RAM model. Now coming to this PRAM model. So this in PRAM, P is basically for parallel. So PRAM stands for parallel random access machine. Okay. So we have to see some fundamental problems and their parallel solution. Okay. So we need to know the parallel parallel computing models are models for parallel algorithms. So this PRAM is basic one. Okay, so we have a PRAM model here where we have n plus one processors accessing a shared memory. Now, what is new here? So in RAM model, what we had? We had just one processor and one memory. Processor was writing something in memory, processor was reading something from the memory, and processor was doing some arithmetic and logic operation. Okay, uh, in it. Fine. So like there were simple basic operations like addition, subtraction, addition. So when it comes to analyzing the algorithms, okay, we assume that time we assume that every simple operation takes 1 unit of time. Like if you are multiplying a and b, what is there? We have one multiplication. So we'll assume that this takes 1 unit of time. Now, if you are doing a plus b, so we have again the assumption that since addition is a simple operation or basic operation, so it will also take 1 unit of time. Although it doesn't happen if you go to the hardware things, your multiplier circuit is more complex than adder circuit. But in designing and analysis of algorithms, we ignore that thing and we just okay assume that if there is a simple operation or basic operation, it is going to take 1 unit of time. Okay, so now coming back to this PRAM thing. So what do you have here? You have a shared memory, you have some processor. So since you have more than one teachers, you can say, to evaluate the answer sheets, so these teachers need to communicate. So here also, if you are deploying the processor to solve some problem, okay, they need to communicate. So now how this communication will take place, we have to see that. So for this purpose we have this shared memory. Okay, so we can see that uh, links are bidirectional here. Every processor is capable of writing in the shared memory, okay, and every processor is capable of reading any cell, okay, of the shared memory. So now how they will communicate? Let's say P0 has to communicate with Pn. Okay, P0 has something. Let's say P0 has some data and it has to be communicated to Pn. So how P0 will send it to Pn. So as you are able to observe that we do not have any communication link. Okay, direct communication link. So what P0 will do? P0 will write somewhere in the shared address space, and in the next step you can say your PN will read it from there. Fine. So uh, basically PRAM model is a shared memory model, and our processors are synchronized. Okay, there is you can say clock synchronization. So DRAM model that we are not doing in our RAM model. That is this communication between any two processors. Okay, so for this communication, we'll assume that if a processor communicates with another processor by writing in a cell of the shared memory, it takes 1 unit of time. Okay, so P0 will write it is somewhere in some cell, and then PN will read it. So we'll assume that this communication takes 1 unit of time. Now, okay. So here, let's take some cell here in the shared memory cell, and let's say it is ith cell, and at the same time, P0 and P1 and P2 want to write something in the cell. Then there will be a write conflict. Both of them won't be successful in writing their data. Okay, any one of them would be successful. So basically what we are observing, we have some certain conflicts here. Okay, so that is a write conflict. Similarly, P1 and P2 may try to read a cell at the same time. Some cell is there that is to be read by P1 and P2. So there will be a read conflict. So for resolving that conflicts, we have certain uh, for resolving read and write conflicts, we have certain variants of the PRAM model that we'll see here. Okay, so the very first PRAM variant or simplest PRAM variant that you can consider is exclusive read, exclusive write PRAM. So what is there in ER EWPRAM? No two processors are allowed to read or write at the shared memory cell at the same time. Fine. What does it mean? Let me go back to the previous slide. So here, assume that there is a cell. Okay. Here you have some cell, and this P1, what will be exclusive read? So we are allowing the processors to do parallel read, but not for same cell. They will be able to read different cells at the same time. So P1 will read a cell. Obviously, at the same time, no other processor would be able to read that cell, but we are allowing other processor to read other cells. Fine. So what you are getting here with exclusive read, our processors are capable of reading different cells at the same time, but they are not capable of reading a cell simultaneously. Fine. Similarly, we have write okay, exclusive write. So what will be there in exclusive write? In exclusive write, processors will be writing their data in different cells at the same time, but they won't be able. We are not allowing them to write in a cell at the same time. So see, don't think that we don't have anything parallel here. We are doing our process. Okay, P0, we can assume that P0 is reading 0th cell, P1 at the same time, P1 is reading 0th cell, sorry, first cell, then at the same time, P2 is reading second cell. Fine. So we have parallel reading by these processors. Similarly, we can have parallel writing. So, and these processors are doing this read or write exclusively. Now, when there is concurrent read, now we can go to we can define or we can say devise another variant, that is concurrent read. So in concurrent read, what we are doing, we are allowing the processors to read a cell at the same time, but okay, the other part where when it comes to writing, we have exclusive write. So we are not allowing processors to read write in a cell at the same time, but our processors are capable of writing, okay, in different cells at the same time. So similarly, the other variant will come where we have concurrent read and concurrent write. So what will be there in concurrent read and concurrent write? We will have exclusive read and exclusive write. Apart from this, we are allowing our processors to write in a cell at the same time, and processors to read a cell at the same time. When it is a read operation, then think, okay, it is very easy. Okay, but when it is a write operation, reading a cell by the processor at the same time is not a big issue. But when it comes to writing, okay, then processors may be having different data. Then there will be a write conflict. So when there is a concurrent write in a cell, then we have to devise some mechanism to resolve the conflict so that we are able of like a processor is capable of writing in a cell. So again, there are certain variants of it. So we have priority CRCW PRAM variant, where we assign fixed, obviously distinct priorities to the processors. Okay, so let me go to this. So what you can do, you can have some priority order, like you can make P0 uh, uh, with the highest priority processor, then P1 next highest priority, then P2, then Pn. Okay, so it will be a write operation. Then since and all the processor want to read write in a cell, then only P0 will be successful. Why? Because P0 is the highest priority processor. Fine. Similarly, the other way to resolve the write conflict is like we can allow a processor randomly to write. Okay, so that is arbitrary CRCW PRAM variant. Or we can have we can have situations where processors that want to write in a cell have same data to write. So in that case, okay, let's say this P0 and P1 and P2 want to write in a cell and they have same data. They both of them want to write one here in a cell. Okay, so since we are observing that they have same data, so we can allow any of the processor to write in the cell. So these are different variants of PRAM model. Now I am taking very basic problem, we can say a fundamental problem. Okay, so Boolean R of n bits. So those who will be knowing Boolean about Boolean R, for them it is very easy. If any input, okay, we have n inputs basically, and if any input is one, our output is one. Okay, so we define Boolean OR operation like that. So what is there in the problem, Boolean OR problem? Basically, we are given n bits. So those who are from non-CS or IT background, electronics and electrical engineering, also people also these bits. Okay, they will be familiar with bits. So either we have 0 as input or 1 as input. So basically, bit stands for binary digits. Okay, so if you have to get, okay, so now you are given an array containing n bits. So if any bit is 1, your output has to be 1. So let's now think of a sequential approach first, a RAM solution to this fundamental problem first. So what will happen? You have if there is only one person or only one CPU, okay, or processing element, then it will take the bits one by one. It will check the first bit, then second bit, then third bit, and finally the result will be given after reading n bits. So is, let's say, if you are able to get the first, okay, your first bit is one itself, okay, then you don't need to read other bits. You can say that you have found this answer, and that is obviously one. Your first bit is one. But in case all the bits are zero, you have a zero vector, okay, all zeros are there in your array, then in that case will be like our will our this processor, our CPU will take the all bits one by one, and okay, so after scanning all these n bits, it will write 0 as output. See how this problem will be solved. Okay, so you can see that if it is a sequential method or RAM model to solve this fundamental problem, then at most our worst case running time is when you are reading all the bits. Okay, so but in best case you are reading first bit only and you are giving the solution. Okay, so now let's see its PRAM solution. So what is there? Just for simplicity, we are assuming that there are n processors. Number of bits is also n, number of processors is also n. Let me go back to this. So here we have n plus 1 processor. So you can ignore this time P0. Okay, so just ignore P0 and assume that P1 to Pn are there and n bits are there. So now what we'll do with this model, we will ask P1 to read the first cell, okay, first bit. At the same time P2 will be reading the second bit, at the same time P3. So you can say in parallel Pi will be reading ith bit. Fine. So at the same time all the processors are reading, okay, a particular okay, their respective cells. So now what happens if any of the processor like okay finds a 1, then that processor will try to write a 1 as answer. Now if none of the processor finds a 1, then in that case 0 will be the answer. So we can ask any processor to write the answer. Okay, so now what happened? P1 to Pn read n different cells at the same time, and so since the okay, so our processors are reading the cell at the same time, and they are doing just one compare. They are checking whether bit is 1 or not. If it is 0, then it has got no meaning, and if it is 1, then processor will write 1 as the answer. Fine. So you can so now there is just one or two lines algorithm. You can see it. This is a parallel algorithm. Those who have not seen any parallel algorithm, they for them, okay, I have kept a very simple parallel algorithm here. So how parallel algorithms are written, you can get some idea about that from these two lines. So what is there? We are using some keywords like in parallel. Okay, so we are using in parallel. You can write at the same time. Okay, processor I for I is equal to 1 to n at the same time. But okay, and then you can write if AI is 1, if processor I reads a 1, then here basically we are writing the answer at A0. So now what may be there? there may be one or more processor with one. So we will take the concurrent write model. Okay, and which one of concurrent write? You can take any of the models to solve this problem, but if it is concurrent write model, we can say that we can do it in constant time. In 1 unit of time, the processors have read a one, okay, read 0 or 1, and then in another unit of time, any of the processor is writing a 1 in the output cell of the shared memory. So we have over time on CRCW processor. But if it is EREW or any other, okay, where we don't have concurrent write, obviously it will take more time. So let's not go to that. Let's take some other fundamental problem and see solution to it. I hope everyone understood this parallel algorithm. Okay, so now the other fundamental problem is prefix computation problem. Okay, so let's understand this problem, and then we'll have its sequential solution. After that, we'll go for parallel solution. So uh, basically, we are given an array containing n elements. Okay, so our elements are like x1, x2 up to xn. What? And we are given a binary associative operator. Okay, I hope you know about binary operators and associative rule. So if there is a binary operator that follows associative rule, then we call it binary associative operator. Fine. So plus is classic example of your binary associative operator. So okay.
Sir, unmute yourself.
So I got disconnected. I don't know at what point I got disconnected. Everything was so okay. Let me share my slides again.
Yes, sir.
So I was in. I was talking about this problem, prefix computation
Yes,
problem.
yes, sir. You were
Okay.
example.
Okay. Good. Good. I thought that okay, it got disconnected earlier. Okay. So now the very first element of the output vector is x1. You can see x1 itself is there as the first output. Now, when it comes to the second output, we have x1 ring sum x2. So what this ring sum is nothing but r star is nothing but the binary associative operator. Fine. So second output is what? x1 star x2. This star is not multiplication. Okay, you can consider multiplication as the operator, but here it can be any binary associative operator. Now, the third element is obviously going to be x1 star x2 star x3. Similarly, we'll be giving ith element as x1 star x2 star x3 star up to xi, and in the same fashion, the nth element of your output is going to be x1 star x2 star up to xn. Now let's come to the example. So we have one input array with the elements 1, 2, 0, 4, 2, 1, 1, 3, and our operator is plus. Fine. So what we'll have? We have the first output of the output vector, first element of the output vector as 1 itself. When it will come to the second element, so we have to do x1 star x2. So operator is plus, so we will be doing 1 plus 2. So we have a 3 here, then 1 plus 2 plus 0. First three elements. Okay, so we have some of them three as 3 here. and similarly we'll move for other elements of the output. Now, when you are doing it sequentially, okay, it takes O n time. Okay, so if you have a RAM model to solve this problem, you are going to take O n time. Why O n time? Because we have, if it is a code or algorithm, then we have a for loop that runs from I is equal to 2 to n. You can say, if it is not that, you are going by logic to uh, analyze your algorithm, then it is simply that you are adding first I minus 1 elements of your list to the ith element of the input list for getting the ith element of the output list. Fine. So basically, for getting the last element, you are adding all these elements. So the time taken is what? We can say that we have n cells, or you can consider it as a fundamental problem, that is sum of n elements. Fine. So if it is a sequential approach or RAM solution, then it takes one time. If it is parallel solution, we have to see that. So I have given a parallel algorithm here. So those who know writing sequential algorithm, for them it would be easy to understand. So there is a terminating condition, and that is step one. So if number of elements is just one, so we have to just produce the element as it is. Otherwise, what we'll do, here we are applying a divide and conquer approach. Okay, so something is being done here parallelly. So let's see what we are doing. So now, for simplicity, again we are taking n processors. So what we are doing, we are dividing. Now let's come back to this. So now consider that here 3 to 5. Okay, we have 8 elements. Okay, so you can consider uh, 8 processors to get the prefix sums or this output. So now what we will be doing, so basically what we'll divide this list. So we'll ask first 4 processors to compute the prefix sum for the first part, where we have first 4 elements. So 1 to 0 4 is there in the first part. In the second part of the input, we have 2 1 1 3. So we have first 4 processors that will compute the prefixes for the first 4 elements, and for next rest 4 elements, rest 4 processors will do their prefix sum. Okay, so this will so see, we have 4 elements and 4 processors. So what we are getting, earlier we had 8 elements and 8 processor. Okay, now after dividing the problem, okay, we are using divide and conquer actually. So after dividing the problem, we have 4 elements and 4 processors. So we can further divide our problem as 4 is sufficiently big. So we can, okay, so we can go like this. So when we'll reach to only one element in a part, and at that time we can say that they produce the element as it is. Okay, so now you can say, see step 2, what we are doing, we are asking first n by 2 processors to compute prefixes for first n by 2 elements, that are x1 to xn by 2. And what we are doing, we are storing them as y1 to yn by 2. Okay, so we have final prefixes for first part. Now we have something happening in parallel. What is that? Let's see that. So what this time we are writing at same time. So whenever you have a parallel algorithm, we have some words or keywords like this. Okay, so like in previous algorithm, we have in parallel. Here I am writing at same time or at the same time or simultaneously. You can write. Okay, so at same time, rest n by 2 processors are being asked to compute the prefixes for rest n by 2 elements. So now come to step 3. What do you have? First half of answer is y1 to yn by 2. Second half, so now let me go to the previous one. So now first part where you have computed the okay answer for first part, everything is fine. So up to this 1337, okay, you have correct values. Once, but at the same time, the REST 4 by 4 processors worked on REST 4 elements, so they did not compute this what like when you will be computing prefixes for 2113 will be getting 2347 like this. So what is missing? Whatever sum is there, like here we have some four element first sum of first four elements as 7. So we need to add this to the prefixes that are here. So that we have done here. So what we did here, we are just doing star a ring sum operation of yn by 2. Whatever yn by 2 is there, that has to be ring sum with the yn by 2 plus 1, yn by 2 plus 2, and all that. So this is how parallel computation will take place. Okay, so here we have PRAM solution. Now let's see the running time of this approach. So as we have divided the problem into two parts and two parts were handled at the same time by n by 2 process. Okay, so this sub problem size was n by 2. So we can those who are familiar with recurrence we can use recurrence to derive the time complexity of this parallel divide and conquer approach. So Tn is equal to Tn by 2 plus O1. What this O1 is? So now O1 is the time when we are adding this yn by 2, the last value, last prefix sum of the first part to the prefix sums of the second part. Okay, so since n by 2 processors are there, they can read the yn by 2 simultaneously. Okay, so it can be done, reading can be done in 1 unit of time, and then we can do the writing. Okay, we can perform all these computation, okay, for the second part at the same time. Fine. So O1 is the time corresponding to that. If there is only one element, obviously it can be done in constant time or O1 time. So that this is going to be the initial condition for your recurrence lesson. And when you will solve this, okay, I'm not going to solve the recurrence lesson. The time will come as order of log n. So number of process where n. So we have something known as work done by an algorithm or a parallel. If it is a parallel algorithm, so by a parallel algorithm. So it is simply the time complexity multiplied by the number of process. So it comes to n log n. Now the algorithm that I have given here is not a work optimal algorithm. Okay, now what this work optimal algorithm is, we have to understand that. So in a work optimal algorithm, we have a speed up equal to number of process. So you see, okay, if you have a work optimal algorithm, your speed up will be equal to number of process. Okay, so running time of your sequence, I have defined speed up earlier. Okay, there was Amdahl law, and okay, so we defined speed up as simply Ts by Tp or Ta by Tb. So Ts, what is Ts? Ts is the running time of the sequential algorithm. So we know that sequential algorithm takes O(n) time. Okay, and Tp is the parallel time. So parallel time here for parallel algorithm, we have derived the time complexity as log n. So we will get this Ts by Tp as n by log n. So this n by log n is not equal to number of processor. Number of processor is n, and our speed up is n by log n. So we are not getting our 100% efficiency, you can say. So we do not have a work optimal algorithm. Now, is it possible to write a work optimal algorithm? Okay, for this problem, we can see that. So, okay, things will be more complex and time is not permitting me. So I am skipping many things. Okay, here. So I am just going to another model of computation where we do not have a shared memory. Here we have something, okay, uh, like, like let me discuss about one of these models. So we have a mesh. Okay, so just for simplicity, I am taking a mesh of size p. So what I am doing, I am taking root p cross root p mesh. Fine. So in our mesh, basically each processor is present at a grid point. So ages are basically we are. I hope you are able to get that. Yeah. So I'll discuss the prefix problem over a mess as well. So now, what is there in place of shared memory? We have communication link. Okay, so we have root p rows and root p columns. Each row has root p processors. Each column has root p processor. Okay, so now these edges are communication links and they are bidirectional. And you can think this as a 2D structure. So we are going to we are going to level a processor using tuple ij, and here also we have synchronous computation file. Now we have to see. Okay, I'll not go to here. Okay, so if just it is the first row, we'll call the if you are taking any row or any column, it will become a linear array. So if you are solving the prefix computation problem using a linear array, what you need to do, you need to forward the element to the next element, then next processor, and then next processor. It will happen like that. So if element xi is at processor I, what we need to do in the linear array, we process. Okay, we basically in step j, processor j has to send xj to write and add the j plus one uh, j plus one element to it, and it has to forward it further. So as I told that if you have a mesh of size root p cross p or with p processor, so what we'll do, we'll let's say there are 16 processors and 16. Since time is not permitting, so I'm just giving the algorithm. Otherwise, I could have discussed it with. And okay, and I have another meeting also. So I'm just reading the algorithm and explaining it. So I'll ask row I to come. We'll ask I. So now there are root p rows. So we can consider each row as uh, a linear array. So we'll ask each linear array to compute the prefixes for its root p elements. Now, after doing this step, okay, so something happened in parallel here. Okay, so and how much time it took to do the step one or phase one? Obviously root p, because we have to at most we have to forward the element project with the first processor to the root pth processor, that is the last processor in that linear array. So now after doing this step, we'll ask the processor that are there in the vertical last vertical array, or you can say last column, to compute the prefixes. And after that, since we need to forward the prefixes, okay, so we have computed the prefixes for first four elements using first, if it is a 4 cross 4 mesh, so using first four processor. At the same time, you computed the prefixes for next four elements using the next four processor at the same time. So it happened like that. Now, in place of the shared memory, what we have communication links, so we have to forward the computed prefixes to the next level. So that we'll do in phase 3. Okay, so what we are going to do, we are going to broadcast jet I and root p in row I plus 1. So whatever final prefix value is there in a level, that will be broadcasted to the next level. Why? Because the last prefix sum has to be prefix sum with the elements of the next prefix sums of the next level elements. Okay, for giving the final prefix values. So same thing we'll be doing for other rows. And phase 1 to root p time, you can understand it very easily. Now since we are we are computing the prefixes for a vertical uh, array, so it also takes root p time. Fine. In last step, when you are broadcasting, okay, in that time also it will take root p time. Okay, so first prefix sum that is computed by the first linear array. Okay, will be broadcasted in the second row. So it can be done in root p time. At the same time, we'll send the next prefix sum computed in phase 2 to the third linear array. So it will be done in root p time, and we'll have final prefixes. So you see, each of these phases takes O root p time. So overall running time is going to be O root p. Now I'm going to in the things that there are many things that I'm not going to. Yeah. So if someone is interested in working on parallel algorithms or parallel computing, so there are many research directions. He or she can go for designing and analyzing parallel algorithms for combinatorial problems where we have exponential time complexity by the deterministic algorithms, or someone may be interested in writing libraries or parallel programming. There are many libraries already available like OpenMP, MPI. So someone may be working on okay, maybe working on libraries for images or videos or other data formats. And there are many scientific applications or complex problems that require high performance computers. So he or she, okay, if someone is interested in that domain, then many times physics people or chemistry people, they have complex scientific problems. Okay, so they need parallel computers to solve those problems. So they may also go for learning parallel algorithms or parallel computing. So here you can find a list of books, okay, that you may refer for your further studies or your further research work. Now I invite the questions from the audience.
Any queries from participants? Any queries?
So there were some complex problems as well, but I did not take, as I was able to know that there are people from non-CS background as well. Anyway,
Yes.
I think everyone understood everything or something else. Anyway, so please.
Yes. To honor your contribution in this FDP, Ashoka Institute of Technology and Management, Varanasi, presents you this very difficult of honorable. Such a complex topic you express in a very simple way.
Thank you, thank you.
It will also be forwarded to you on mail, sir.
Okay, thanks.
Thank you, sir, for providing us with such a nitty-gritty. Please share the certificate. It's not visible. It's not visible.
Yeah, I just saw it. Yeah.
It's on the screen.
Yeah, fine, fine. So thank you. Okay, thank you so much, Dr. Kavita, Professor Sharika ma'am, Professor Preeti ma'am, and other organizers. Okay, for inviting me to this virtual FDP. Okay, thank you so much once again. Thanks to the audience as well. I expected a few questions, but anyway, okay. Okay, thank you so much. So I am leaving now.
Thank you. Yeah. Thanks. Further proceeding towards the next technical session of today on the topic Smart Grid Security Threats. Speaker of the session is Professor Dr. Sarika Srivastava. I am delighted to introduce Dr. Sarika Srivastava ma'am. She is Director of Ashoka Institute of Technology and Management, Varanasi. More than 25 years of experience in industry. He did BE in Electrical Engineering from Government Engineering College, Jabalpur, MBA in Marketing, MTech in Power System from KNIT Sultan, PhD in EE. Ma'am is holding various profile in Dr. APJ Abdul Kalam Technical University. She is Associate Dean R&D of AKT. She is member of Academic Council and Examination Committee of AKT. Ma'am is the technical expert in UPPCL, UPRBN and Union Bank India. She has published and presented significant research papers in international and national journal and conferences. Published book chapters in Springer and other international publications. She has got 3 patents to her credentials. She has been associated as resource person in Atal program conducted by AICT as well. Now, I request ma'am to take over the session. Ma'am, unmute yourself.
Am I audible?
Yes, ma'am.
Okay. So thanks a lot for such a generous introduction. And this is going to be the second session of today's FDP. And let me share the presentation first.
Yes, ma'am.
Ma'am, I'm not able to share the presentation.
Wait, ma'am. I'll check it. I will make you the presenter. Yes, ma'am.
So is it visible to everybody?
Yes, ma'am.
So very good afternoon, everybody. And thanks a lot for inviting me to deliver a session on the topic of recent trends in FDP, on the topic of recent trends in computation, data processing and data security. And I appreciate the topic, and my topic of the talk is smart grid security threats, and it's more about cyber security rather than electrical security. So as we know, energy is central to the growth and development of any country, and electrical energy consumption is intensifying. And as far as the resources are concerned, energy resources are concerned, energy sources are depleting, and entire system is forcing towards the solutions which are more sustainable, like renewable sources based on like solar, wind, and other sources which are posing less threat to the environment. If we talk about the automobile industry, it's shifting from ICE to EV. ICE is internal combustion based, engine based automobiles, and carbon footprint has to be reduced. That's why entire world is moving towards electric vehicle. Electric vehicle integration to the grid is another challenge. So entire system is very much demanding, and we need to upgrade the existing infrastructure. So if I talk about the conventional power system, we have age-old power system, and there is strong need to upgrade the existing system because of the forcing issues in the power industry. We have to modernize the traditional power grid, and we are expected to make it more efficient. Losses should be less, system should be more efficient, performance of the each and every component should be more reliable, and as well as this entire system should be sustainable. And what is the solution? It's going for, it's nothing but smart grid. So as far as smart grids are concerned, they are governed by advanced computing, control technologies, as well as networking infrastructure. So it's not about power system only, it's about very high complex computing, complicated and very systematic controls technologies, as well as networking infrastructure. It requires a very strong infrastructure to make the things happen. There are so many threats to the smart grid, like physical attacks, cyber attacks, and natural disasters. These are some of the main threats to the power system. And these cyber threats are not limited to a small section of the entire system. It may lead to infrastructural failures. Suppose some threats are there, cyber threats or cyber attacks are there in the generation of the system, generating part of the system. So it may lead to a major a major portion of the system will be cut off, and there may be these conditions of blackouts. We know a lot of energy theft, power threats are going on, and we have to control them as well. And everybody has got smart meters at their home now, so a lot of data is being fetched from the customers, and their privacy can be breached. So there are so many issues, endangered safety of operating personnel as well, some wrong communication, some kind of wrong initiations from people who are having wrong intentions. They make the system very risky. So it's not a matter of the security of existing energy system only. It affects, it impacts the national security as well. So we know Ukraine Russia war is going on, and their power systems and the grids are being attacked. So one of the easiest ways to attack their information system, their computer networks, etc. So what are the various factors that are affecting the performance of existing grid? Is increasing demand of electricity. We know it very well. So a lot of development all over the world is going on. We are leading a better life, more comfortable, energy-centric life. So it's population is increasing. So all such things are leading to increased demand of electricity. We have supply short of electricity. People are more, demands are more, and supply is less. We need to reduce the losses. The structure of the power system is age-old structure, transmission and distribution, and there are significant losses in it. It's leading to reduced efficiency. We have to have some measures to reduce those losses as well. Peak demand management. So throughout, if we talk about the throughout the day kind of profile, load profile, demand profile. So some of the hours, like evening hours, demand is maximum. Everybody is requiring more energy. So how to manage those peaks? It's another factor which is forcing towards smart grid solutions. For the sustainable development and to reduce the carbon footprint, integration of renewable energy generating systems, distributed energy sources are being done. So microgrids are basic building blocks of any smart grids. And distributed energy sources are mostly based on your PV, wind, and other renewable sources. So they are not at the point of generation only, they are now the part of distribution as well. Further, international issues are towards we have to take care of sustainable development, environmental issues. There should be solution for global warming, effective use of electric vehicle. Electric vehicles they are the future. So there is no nothing like that we can escape from it. Internal combustion based engines are going to be obsolete very soon, and the electric vehicles are going to replace them. So there are issues with electric vehicles. Electric vehicles are going to take a lot of energy from the grid, though they can also be treated as a pool of batteries. There, if so many electric vehicles are integrated, they are in a parking, and we can supply that energy which is stored at the in their batteries. It can be fed back to the grid. So if we have to use the electric vehicles effectively, we have to go for smart grid solutions. Customer satisfaction. Customer should know how much energy the person is consuming, what's their rate of consumption, what are the peak hours. All such things are requiring for these are the factors which are going to change the pattern of existing grid. If there are a difficulty in meter reading, so smart meters are there. Poor efficiencies of conventional power generation systems like thermal power, nuclear power systems, also diesel based systems. So these conventional power systems have poor efficiency, so we need to look for alternate solutions, and new business opportunities are there. So all such factors are looking for, they are affecting the performance of existing grid, and we have to transit we need to change the system towards smart grids only. So what is a smart grid? What makes the grid smart? So digital technology that allows for two-way communication between the utility and its customer. So what is utility? It's which is giving supply to the customer, and there has to be sensing along the transmission line what makes the grid smart. So there are throughout measurements like phasor measurement units are there, different control centers are there to for the continuous measuring of various parameters of electricity, any condition of fault, real-time monitoring, and corresponding efficient control. So it's power grid along with ICT. ICT is nothing but information and communication technology. So power grid along with information and communication technology makes smart grid. So though it is electricity network, it can intelligently integrate the action of all users which are connected to the generators. Am I audible? Okay. So it is able to integrate the various components of it, whether it is generators or consumers and various devices, for ultimately leads to efficient delivery of power with sustainability, economically, and secure system. So overall communication network of the smart grid connects three major components. One is grid, another is service provider, and customers. So what is grid? Interconnection of various power systems. So a regional power system, there is state grids, regional grids, and regional grids are connected together to form national grid. The communication among these components govern based on the different channels and protocols. So there are so many communication channels to communicate amongst themselves, to communicate between generating system, grid, and customers. Two-way communication between different parts of the system. Large scale energy generation, energy distribution, energy transmission takes place at grid domain level. So we know smart meters are already there. New energy sources are being integrated very on and off. Sensors are there throughout the system, IoT and RFID sensors are there in the entire system. So many control devices are there. So all such things are making a revamped ecosystem. So some of the features of a smart grid are increased renewable energy. With the help of a smart grid, what is possible? To integrate more renewable energy based sources. A lot of policies are there in every country. They have got renewable, they are promoting renewable energy like anything. And India also, we see that a lot of the solar energy based programs, wind energy based leverages are there. And with the help of a smart grid, it's possible to integrate these intermittent or sources with grid efficiently. We know that the efficiency of the existing system is less on what is expected. To improve the system, we have to increase the efficiency of different sources and we have to reduce the losses in transmission and distribution. Further, the losses occurring in different generating sources. Better reliability. A lot of measurement and control devices are there, and they are able to detect the faults by the continuous measurement of various parameters. It's possible to detect the any abnormality in the system quickly and act accordingly. Such things will prevent the system for leading into any kind of catastrophic disasters. Further, increased customer participation, like two-way communication is possible. So customer will be more participating. And enhance security. It is a question whether with the help of a smart grid, security will be increased or it's going to be compromised. We need to work. Now there is why this session of smart grid security is introduced in this FDP of computer science engineering, because this is the time that we need a lot of multidisciplinary and interdisciplinary research. So if we talk about power grid, it's not all alone about power only. It's about information technology, it's about communication technology, it's about electronics, it's about infrastructure, we lead into mechanical, civil and everything. So we need to work together, and there are security threats. Every equipment, every point that we are adding into the system will increasing the insecurity of the system. So where we are expecting that is a smart grid provide a more flexible, efficient and secure electricity infrastructure, enabling the integration of renewable energy, reducing energy waste, improving reliability, and empowering consumers to take control of their energy uses. Out of these features, we can summarize it. But we have to do a lot of work for enhanced security of the system. If I talk about traditional grid, there is one-way flow of electricity only, from generation to transmission to distribution to consumption. And naturally market and operations will be there. So it is centralized and bulk generations were there, and a heavy reliance on coal and oil. As we know, still a lot of participation of conventional energy resources are there, and gradually we are shifting, we are penetrating more renewable based energy sources. Limited automation in the traditional grid, automation is limited. All the sensors, all the protective devices, most of them are uh, electromagnetic type, and now we are shifting towards automation. A lot of work is going on, we are not lagging behind, but aggressively we have to work together. Limited situational awareness is there, and there were consumers lack data to manage energy uses. Every month, and once in a month, we used to get electricity bill. That's all we used to have any kind of communication with the utility. If I talk about the future grid or smart grids, it's going to have two-way communication of electricity as well as information. It's not about electricity only, it's about information too. How two-way communication of electricity? Like solar power plants or solar panels, they can take the power from a grid to when electricity is not available, then solar irradiance is not available, and they can feed the energy back to the grid when there is surplus of energy. Same is true with electric vehicles as well. Electric vehicles are able to take the energy from the grid, as well as they can feed back their energy stored in batteries to the grid. And for such things to happen, strong communication infrastructure is the backbone. So there are various levels of control. Transmission control centers are there to control bulk electricity generation. There are electricity transformers to change the level of voltage. Substations are there. And after reducing the level of voltage, electricity is being distributed to different people, like offices, cities, for industrial purpose and all. So at one end is transmission control center, and we have distribution control center, and all such things are managed together centrally by supervisory control data acquisition, that is a SCADA. So if we compare both the grids, existing as well as a smart grid, so whereas existing grid is more of electromechanical in nature, smart grids are digital. One-way communication is possible in case of existing grid, and smart grids are with the help of smart grid, two-way communication is there. Centralized generation, here distributed generation, limited sensors are there, and here so many sensors throughout the system. Sensors are implanted. Manual monitoring, here self-monitoring is there, and all better control, self-healing. These are the main features of digital smart grids. So these are the, if I talk about the conceptual model of smart grid, we have got various domains. One is bulk generation. After generation, the next connection, electrical connection, is transmission. After transmission, we have to distribute that energy to various users. So distribution infrastructure is there, and then comes customers. All further, we have service providers, because energy is produced by so many players. So there are various service providers. All such operations are need to be controlled. There is market. So there are private players as well. So whomsoever is able to cater the demand of people at right price at right time, they will be benefited. And to make all such things realize, secure electrical as well as communication interactions are required. So these are the domains, various domains: market, operations, service providers, customer, transmission, bulk generation. Electrical connections are there between bulk generation, transmission, distribution, and customer, but communication interfaces are there everywhere. Market, it is depending on the demand, depending on the market, two-way communication is there between bulk generation, transmission, distribution, as well as customer. Operations are going to connect with everybody. If we talk about service provider, it depends on the demand of the customer. They have to provide the energy at right price. So operations are there, centralized operations are there to communicate with all the players, all the domains, and give correct instructions and for efficient and reliable supply of the energy. Major components are of smart grids are smart infrastructure, smart communication, smart management. It's very much it is central to the entire system. Smart protection is very much required. So these are the main components. Any smart grid will have these 4 components, and in smart infrastructure is the backbone. It will have further 2 parts. One is smart energy system and another is smart information system. So while smart energy system will have generation, transmission, and distribution, it's not about hardware and components only. They will have software, information exchange, interfacing softwares, interfacing infrastructure as well. And smart information system consists of smart metering, sensors, phasor measurement units, PMUs. They are able to continuously monitor the condition of various parameters under the normal condition and under the condition of abnormality or the condition of fault as well. Based on such parameters, you can take the right decisions. You can prevent the percolation of fault to the remaining system, and accordingly, the protection system of the smart grid will take the action. And information management. So a smart information system will have these 4 components. So what's the function of information and communication technology in generation, transmission, and distribution? In generation domain, automation of bulk generation and distributed energy resources operation, synchronizing and adjusting the voltage level. There are, if we connect new generating devices, if we disconnect the generating devices, there are more loads, different kinds of loads. So voltage levels has to be maintained. So this is the work of ICT in generation domain. In transmission domain, automation of electricity, a transmission grid, power transmission grid is performed through SCADA, supervisory control and data acquisition, or energy management system. So both the things are there in case of transmission domain. So ICT, here very strong infrastructure is required for controlling the entire system. In distribution domain, in distribution domain system, it improves the classical outage management system by automation. So earlier the system was manual, and now it is a lot of automation is there. So a lot of work has been done in case of in the field of distribution. And real-time adjustment by advanced distribution automation. Real-time data is being taken, and accordingly corrective actions are being taken. So how does a smart grid work? It serves as a control center that manages electricity generation. It distributes electricity to various households, industries, commercial areas, and social infrastructure. It integrates information technology, operational technology, and advanced metering infrastructure, AMI. And the entire controlling and management of these components is being done by smart grid. So there are three categories of smart grid devices. One is operational technology that refers to hardware and software controlling and monitoring industrial infrastructures, physical devices, and work processes. Here, these are the smart devices. Generator, transmission line, transformer, loads, various state estimators, physical system, cyber physical system components, controllers, lot of various controllers, complex controllers are there to control the mechanism, HVAC controllers. These are OT devices, and IT devices are, you people are the people from computer science background, they may relate with these terms rather than people like us. Server system, router, network node, storage system, system memory, CPU, network hardware resources, DNS, wireless communication, authentication server. So these are IT components. So you can see too much of information technology is involved in smart grids. And AMI, advanced metering infrastructure, has smart meters, vehicle to grid, V2Gs, vehicle to grid devices. There are various electric charging systems are there. Electric charging infrastructure is increasing at a very rapid rate, and phasor measurement units are also there. They are also part of advanced metering infrastructure. So due to integration of these components, electricity is efficiently managed and transmitted. So these are the components. There are hardware, software, there are some system software, and there are some network software. So substations, transformers, meters, sensors, automatic controllers, they are required for the interaction. Intelligent interactions are required. They need to communicate together with each other for coming to right solutions. The software realize the functions of dispatching. We have to dispatch the electricity to different parts, to different regions, to different sectors based on their priority as well. There is an intelligent defense system, intelligent energy storage system as well. Spinning reserve is there. So to manage all such things, softwares are required. And network softwares. Network softwares are required to have interactions among all components. Network softwares are very much required. They play a very significant role for timely and interactions and right decision making at the right time. So we can see that the grid is no longer a closed system. It is it's an open system. It's a combination of factors to achieve. We have to consider a lot of things to achieve smarter generation, transmission, and use of electricity. So interaction-based flow mainly include electrical energy, data generated by hardware and software, and various networks for data action. So the interactions, lot of interactions are required, and lot of analysis of data. Big data is another area in the smart grid. With the help, we are measuring so much of data. with the help of phasor measurement units, various metering devices, smart meters. So that data is being stored somewhere in cloud or in some servers. So how to handle those data, and how to take right decision, how to forecast the future demand, how to forecast the generation, and take appropriate steps, whether increasing the generating infrastructure or advancing the transmission infrastructure or modernizing the distribution devices. So everywhere interactions among all such hardware and software is required. So there is power flow, data flow, control flow, and information flow. So all such elements, their intrinsic interactions, lot of interaction is leading to cyber insecurity. So we saw that power grid is it's a huge system. It's complex. Because of a variety of components integrated to it, it's quite complex system. It's critical. We cannot think about living without electricity. So it's critical. It's expensive. So, and we know that a smart grid is composed of power grid and ICT. And ICT is one thing which is increasing the vulnerability of power grid. So cyber grids, smart grids are prone to cyber insecurities. While IT technologies are very much required, we cannot think about smart grid without IT technology. With the help of IT only, it is possible to have real-time monitoring of the system, and advanced information analysis and automatic control as well, smart actuators, smart healing. But all such devices, their nodes, their points make the system vulnerable. Each new device entering the electric grid is a potential access point for bad actors. Are you people able to follow me?
Yes, ma'am.
Okay. You may interrupt at any point if you feel so.
Sure, ma'am.
So there are various security threats. I am not considering about the kind of faults which are there in smart grids, electrical faults. I am not considering much about it. I'm talking about information technology or computer or cyber security related threats only. Smart grids are prone to security attacks at various tiers, as we saw that there are various points where from where the threats are possible. Through those sources, threats are possible. There are pathway for attackers to exploit vulnerability and introduce additional threats in crucial situations such as natural disasters, terrorism, and theft. They can play with sensitive data of the customer, the rivals. There are a lot of malware propagations. There were so many malfunctioning ransomwares are there. Recently, we saw a few months back only. I think the last year itself, one attack on a US system, ransomware, and in other part, in every sector, every day there is so many number of cyber crimes going on. So the smart grid is not aloof from it. So a lot of malware related or virus related or ransomware related attacks are being done, and the security of the system is being compromised. So communication equipments are there throughout the network. So they are a big threat to the cyber security. False information may be fed in the systems. There can be attack on the SCADA. If some attack is made in the supervisory level, it may lead to bigger disaster. Modifications are possible. Many other attacks related to cyber security may be there. So there are various challenges related to cyber security. Smart grid rely heavily on digital technology and networks and making them vulnerable to cyber attacks such as hacking and malware. So some malware, some virus may be injected through mails or through interactions. Hacking of the server, hacking of the systems may be done. A lot of sensitive information about customers, about the energy usage based information are being targeted, and the mishandling of these data may lead to cyber crimes by the criminals for their financial gains. As we know that there are various components of smart grids, and multiple organizations are owning them. They are being handled by different organizations, and controlling such a big system and standardizing such system is not possible. It's not easy at all. So it leads to bigger risk. Privacy concerns. Smart grid systems collect or store large amount of data related to customer, and it may lead to by seeing the pattern of consumption of customer, like if some hacker hacks the information of customers, they may draw the conclusion that at what the person is not available in the house, and at what time they are consuming more energy than they are sleeping. We have got so many points like TV and everything, and we don't know how much data we are exporting, how much confidential data we are exporting. So based on those data, malicious if malified intentions are there, people may take advantage of them, and they may disturb the entire system. Lack of standardization. As we talked, that different vendors are there, standardization is not possible because there's so many players are there. If we talk about power players, generating companies, and distribution companies, and communication system, information technology, a lot of vendors are there, and correcting them on a common platform, it's very difficult to have a common standard rule for them. Though there are grid rules, so grid interconnection rules are there, but still stringent control is required. Then only we can expect a better system, better and secure system. So they have interoperability issues between different devices. A lot of interactions are going on between different devices and systems. As we know, lack of trained personnel are there. Though our country is producing a very large number of engineers every day, larger number of technical professionals are being produced, but we know that we lack the trained professionals. So if the person is not trained enough, person is not having a right knowledge, right information, right technical skills, the steps taken by them will also be compromised. And system is depending on third party vendors. So it's controlling them is a big task. So there are further challenges. Data information security requirement. Large number of smart devices are there. Security in supply chain. We have international cooperations as well. Some of the meters, some of the exchange of power is going on with neighboring countries as well. So we have to take care of their rules and regulation. There is standardization as well. So coping up with international exchanges is further a big problem. Large number of stakeholders are there, and lack of awareness. It's going to ignorance is not a bliss. There were so many global smart tech attacks on smart grids, so it's not something very new. We heard about so many attacks on different system, and I have taken the data of some previous years only, but this was the first detected attack, cyber attack. In 2010 in Iran, it disrupted the nuclear centrifuges. The working of nuclear power plant was affected, and the virus that affected the system was Stuxnet. Nearly one-fifth of Iran's nuclear centrifuges were destroyed. The worm infected over 2 lakhs computers and damaged 1,000 devices by targeting industrial control systems. So we can assume how fatal was that attack. And it's going on every day, everywhere, somewhere, some kind of cyber attack is going on. And it's in Arizona, in Korea, in Israel. So these are various methods. Malicious code was introduced, and black energy malware was there. And one major attack it held in 2017 in Ukraine. It was very fatal one. Again, it targeted nuclear power plant. It led to an abnormal operation of the system, and 65 GB of sensitive data was stolen. And in 2020 also, during the period of COVID, there were so many attacks, and NPP, Energia, Portugal, NL groups, blackmailing softwares, intranet connections. So we can see these cyber attacks are quite fatal to the system. So these are some recent attacks. In April 22, Ukrainian energy company Industry Industria 2 malware, and directly connects with electrical utility equipment to send commands to the substations devices that regulate the flow of electricity. So it lead to denial of services, DOS. So it affected the utility directly. So definitely its impact is going to be more severe. Texas energy market failure in 21 only. February's big freeze winter storm vulnerable to Texas energy market failure. So we can see that we cannot ignore the threats. We have to take strong actions. We have to make the system more secure. So there can be different types of cyber attacks, type 1, type 2, and type 3. There can be in generation, distribution and control, and consumption. So cyber attacks in generation system is type 1. Cyber attacks targeting distribution and control systems are of type 2. And type 3 is consumption. So further, easier to hack, which is most easy to hack. It is most difficult to hack, and it is the most, type 3 are easiest to hack. That means consumption part is easiest to hack. Largest scale to be effective. Hacking a power plant is hacking multiple thousands of meters. If somebody hacks a power plant, it's a biggest thing. So definitely it's equivalent to hacking multiple thousands of meters. While hacking the meters is going to affect a smaller portion of the system, but hacking a power plant is going to lead to a big threat to the system. It may lead to security of the country as well. So this type of attack is the most severe one. It affects the operation of generators. Turning off a non-generator can imbalance supply and demand. Definitely, if somebody is able to take control of the generation, there will be disastrous impact. Ripple effects will be there, and there will be it may lead to due to physical access or cyber access. It is possible that the generator controls unit is being hacked, or it is accessed remotely, or direct physical access is also possible. Next is type 2 comes under distribution and control system. These kind of attacks are central to control and monitoring central. Attacks to networks, even it may lead to very dangerous situation with the help of wrong communication, wrong control, wrong misleading information based on monitoring, may lead to wrong impaired decision. And the type 3 is customer side, that is advanced metering infrastructure, home area network. So here utility center, markets, and different customers, they may be targeted. And combined cyber physical attacks can also be there. Bigger ones like any mix of type 1, 2, and 3, type 1 and type 2, type 2 or type 3, or all together, as well as physical attacks. So there will be major damage. I know time is approaching, so I will quickly cover the things. So these are some of the potential impacts to utility. Denial of service is very, very important against availability of the network. If this were to happen in a smart grid, it will lose the connection to countless devices. So it is the biggest threat. Malware propagation. Attackers develop and inject malware to manipulate functionality of the system. It's very common. Ransomware is very dangerous. According to cybersecurity ventures, global ransomware damage costs are predicted to reach $10 billion by 2027 from just 320, while it was 325 millions in 2015, it's expected to cross 10 billion by 2020. So I'm a very small person, but 2 years back, one ransomware attacked my system, and they asked me for ransom of $450, and I lost data of somewhere around 150 GB. So I couldn't afford to pay that much of a large amount of data, because luckily some of the important data was backed up in time. Otherwise, still I lost a lot of useful information as well. So we can understand, if it's important information of such systems are hacked, how to handle it. So there are security levels, sources of threat, causes of threat, and attacks as well. So 3 major requirements are availability, integrity, and confidentiality. So we expect that the information should be available in time. Integrity, unauthorized access should not be there. Confidentiality should be there. True identity of the communicating party should be there. And providing permission and granting access to the system. And any action performed by the user cannot be denied later. It's a right at once, well as is going to be there. So let's come to a quick look to the solutions. So you people are here, a lot of people from computer science and engineering, from information technology, from electronics and communication and management. So potential solutions for cybersecurity in smart grids are based on blockchain-based cybersecurity, AI-based cybersecurity, deep learning, machine learning. So while blockchain is able to have the capability to apply to smart energy system to self-regulate and mitigate cyber attacks, it's able to improve, AI is able to improve reliability and robustness. That means we will get uninterrupted supply, and deep learning based models are able to provide meaningful feature extractions, like based on the data fault patterns we can think of right steps for the protection system, what kind of advancement and protection is required. Such kind of decisions can be based on the deep learning networks. ML is being used in smart risk extensively. It prevents the system against smart cyber attacks, as well as for the load forecasting and for future demands, electricity prices. We can use machine learning based systems. So the people who are doing a lot of research, they may address such issues. They may land into collaborative research, interdisciplinary, multidisciplinary research with their colleagues from different departments to to find the solutions for such threats. So there are various solutions. One is network security, because network is there throughout. So the foremost is denial of services detection. So smart grid must detect DOS attacks as soon as it happens. So there are some methods of it. It should be able to take appropriate action. It's not only finding the problem, it's about taking the right decision at right time. So there are some methods of mitigation as well. Data security, data has to be protected, authentication should be there, and cryptography methods are to be used. Data has to be encrypted, and there has to be authentication software, authentication keys to to have data integrity. It's a same part of it. Key management plays a significant role in authentication and encryption of secure system. So public key infrastructure, symmetrical key in management, network security protocols, all such things are steps for solutions. They will prepare the system for against any of the cyber attacks. And back to smart metering and privacy case, to avoid third-party access to metering data encryption at the smart meter, so people any malified intentional person cannot access the data encrypted in smart meters. Message like credit cards, whenever we do any credit card transactions, we get some kind of alert. So same has to be true with smart meters as well. So further power system solutions are also required. So we can conclude, due to time constraint, I have to rush towards end. So security over the grid is no longer maintained by one user. There are a lot of players, lot of devices are there, whether it is power system based devices or communication or computer or information technology based systems. And so there has to be a collective responsibility as well. To leverage the benefit of interconnected resources, companies must invest in cybersecurity programs to protect from vulnerability of a smart grid. So each and every company, whomsoever is participating, they should have some mechanism, some program, some address to handle issues related to security of the system. So there has to be a structured system of security, and it's better to have minimum exposure to threat. It's better to have a preventive mechanism rather than corrective actions. And We know that landscape is evolving rapidly. The entire system is changing at a rapid rate. So we cannot expect the industry is standard, and then continuous effort to handle such issues are required. So thanks a lot for patient listening. These are some of the references. Definitely we can make this world a better place. More, we expect brighter, cleaner and greener planet. So if you have any queries, I'm here.
Participants, any query please? Ma'am, to honor your contribution in this FDP, our institute presents you this certificate, honorable mention. It will be forwarded to you on mail. Thank you, ma'am.
Thanks a lot. Thank you so much. Thanks to all the participants and my old colleagues, present colleagues, and the presenters, moderator, everybody. Thank you so much. Thanks a lot.
I hope this session will motivate and help our participants to proceed for their research work in the area of smart grid and security threats. Dear participants, now we come to end of today's session. I request participants to fill their attendance in the link provided in the FDP WhatsApp group and forward it to their mail. Thank you everyone for joining. Have a good day ahead.